Okay, I was muted for a little bit there. Oops. That's a little loud. Turn that down. I want to say I wasn't muted for that whole time, but who knows? Maybe I was. I don't think I was. Anyway, we gotta start by doing the problem. Gotta read the. Okay. Just fucking get on with it. Okay, so a 3 kilogram. Okay, we're in non-American, the better system. Rest on top of a 2 kilogram block that's supported by but not attached to. Okay, the upper block is suddenly removed. Determine the maximum speed reached by the 2 kilogram block and maximum height. So what we'll do is we'll probably find this speed and then we'll do some kinematics to see how high it goes. You need my live reaction. Sure, I'm here, I'm live. Okay, that was... Wait, what? Why is my mouse only on the... I need to move which monitor my mouse is on. 1 second. I thought I... What? That's so weird. Oh, okay, it's incorrect. That's why. Come on, please, please work. My tablet has been like... Oh, it's working. There we go. I DM'd... Oh, you DM'd me something. Okay, let's see. What's this live reaction? Is this image? Oh my gosh, what the heck? Wait, that's so cute. Wait, that's so cute. What, is that live 2D or is it, something else? It looks like it's gotta, like... Wait, or is that just like... I can't tell what program that is. It looks like it's tweened. Oh, that's live 2D. It has to be live 2D. You're moving your head. Wait, that's so cute. Oh my god, the little emotes. That's so cute. What the heck? I would show it. I don't know if you're like waiting to show it on stream. I'm not just gonna like show it without you saying something. That's so cute. Oh my god. That's so hype too. Umbra streaming. Or actually, maybe you do stream and I just have never caught it. I'm gonna be real. I don't have a lot of time to catch streams anymore. Maybe it's just me being a silly head. Okay. I haven't streamed in months. Okay. Whew. Dodged a bullet there. I figured, because I remember getting notified when you were live for one of your ones you were actually live for. I was like, I'm pretty sure I would know. Metal Pipe, thank you so much. I love you. I love you forever. Where would I be without Metal Pipe? I really need to like make... I think this should just, instead of this problem being blocks, I think they should just be metal pipes. Or it should be like me sitting on there, you know? Like, here's a picture of me. This is Damie distilled down to one singular image. That's beautiful. I love metal pipes. Okay. I guess I should probably define some gravitational potential. That might be a good spot. Probably like here is 0. This is state 1, and then like up here, this is state 2. We gotta define like our 2 states. I didn't know. I just started. Hi, how's it going? I keep looking this way now to check my monitor. I had notifications turned off. Oh, that's fine. You're never beholden to make it to any of my streams. I'm just a silly cat boy. Oh god, okay, so we need to determine the maximum speed reached. This is gonna be like kind of tricky, is the thing. So we know that's gonna have some potential. The thing is, like, we don't know what potential it's gonna have, because we don't know how high up it goes. That's the second part of the question. So like, probably not something we can solve for initially. It's gonna have some elastic potential for sure. T0 is gonna equal 0 because that's 1/2 mv0, and that's 0. So that's a good start there. And we know that T final kinetic energy is going to be what we're looking for. So T final equals 1/2 mv squared, v final squared, and this is want v final. So that's a good start too. So we can find some of this spring potential energy, which is all that it's going to have at the beginning. So we might have to... I'm so hyped for Damiecraft V2. I am also hyped for Damiecraft V2. I would like to do that. Realistically, it is going to be after... What's the date that I can give? What date is that? It's going to be like definitely after mid-February at the earliest. But honestly, I actually have a very light quarter, which is like kind of awesome. So I may be able to actually do Damiecraft before I go on break, which I wouldn't mind doing that. Okay, so I think I actually want to write this out as a bunch of initials and a bunch of finals instead. If we say like VG initial, this is going to be 0, plus VE initial, this is going to be something, plus the U, plus T initial, that's going to be 0. You want to do the, if it's before April, I'm fine with it. Yeah, it's probably before April. I mean, okay, granted, like, I probably won't be able to play a lot. I don't really know. I do not have, oh wait, we might have to do a system of equations for this. Anyway, sorry, I'm just thinking. I don't have a lot of, like, brain power to be able to do that. Okay, so we don't know what this is, and we don't know what this is. Wait, Rev, you're gonna get a master's? Wait, that's crazy. I mean, crazy like in a good way. Oh my gosh, I didn't know you wanted to get a master's. I probably won't get a master's. There's a timeline where I do, but it's kind of not a timeline that I want to have happen. Wait a second. Okay, wait. So it's with a spring constant of... Wait a second. I don't know how much this spring is squished. You need a... Oh, you gotta go? Bye. Your college schedule is always insane, so I can work around with that. You need a master's or higher to be a licensed for psych? Oh, whoa, I didn't know that. That's crazy. Well, they just let anybody be an engineer, so you don't have to worry about that. Okay, so this is kind of weird. The spring is gonna get squished by how much spring springs away. Exactly. The spring is gonna get squished depending on how much weight we have on top of it. Wait, am I solving? Wait a second. Sorry, is this cut off for you guys? Am I solving problem 3.27? I think I am. Okay, wait, so we have to assume that it's attached to the spring? Oh no. Okay, so we have to like, okay. I need to draw some free body diagrams, okay? So the 3 kg, we're not gonna really have anything that's interesting going on there. Let's draw the 2 kg. Till 2 kilogram. So we've got this weight, right? This is our like mass of 3g, and we have its mass. This is mass of 2g, and I guess I could just write 2, but whatever. We have a normal force, or no, we don't have a normal force actually. We have a Ah, yes, we have a spring force. And we know that it has a spring constant of Newton meters, which is great. Okay, maybe I can't do this with work. Well, maybe I can't do this with work energy? But I feel like, okay, like maximum speed feels to me like a work energy type beat. Because if I just did it with forces, I could get an acceleration. Actually, no, I probably have to do that with work energy. I am confused. Just for reference, chat, like we haven't done any of these. Ah, I'm so pooped. Oh, hey, Egg, how's it going? We've done like one problem, and it was like easy mode of work energy. So these are like kind of... My brain is, sup? It's going well. Maybe not well, it's going. I'm trying to figure out, there's something we need in between here, because if I want to calculate the spring potential, I need to know how much the spring is displaced. I guess we could say that... Well, we don't know how much the spring is displaced. Oh, wait. No, we don't. I was going to say the amount that it's displaced this way will be the amount that it's displaced this way when it reaches the maximum height. I don't know if that's true, is the thing. I don't think it's true. Oh boy. This is complicated. Okay. Let's think. What would be the better way to do this? We can figure out... So we know that it's in equilibrium. Ah, maybe that's what it is. We know that this is in equilibrium. So we can figure out how big this spring force is. Okay, now we're cooking with gas. That's what we needed. That's what we needed. Okay, so when this is squished down, right, it's like not moving. So when 3 kg plus 2 kg spring, or like statics, I guess. My handwriting is gonna be really bad. The answer is 5. The answer is, wait, I can look at the answer. If it's 5, I'll stop streaming right now. The answer is not 5. Neither of them are 5. I would have just turned off the stream and be like, okay guys, the answer is 5. We're over, we're done. I'm really glad it's not 5. Why is my music not playing? Oh, it's Pikmin. It's very quiet. I forgot. You guys can't even hear it. They're too quiet. Okay, I gotta skip past Pikmin. Okay, we got Paper Mario. Sorry, wait, I'm on Twitch? Yeah? We're all on Twitch. Okay, so FS. This is great. Okay, so FS equals... because then we can do displacement. Oh, lol. Me. That's so real. Okay. 3 plus 2, I almost wrote 5, times 9.8. Is how big our spring force is, okay? That's a big win, everybody. We just found out this beautiful gentleman's credit card number. It's 49. I don't know how that's his credit card number, don't ask me. Okay, so we got 49 newtons of spring force. That means that that's gonna act on our... thing. Okay, sorry, my brain stopped working for a second. So, okay. We know that there's, okay, we need the maximum speed, but I feel like this is gonna be our maximum height. I love finding out beautiful man's credit card numbers. Okay. Yes. I also love that. Okay. So spring, I don't think we have any applied forces because I think we're gonna have to solve for, no, we need to, oh, can I cancel out? Maybe I can cancel out the x's. Okay, maybe we just leap of faith this. I think we just leap of faith this. Okay. So let's say that, so this is the integral of 49 times the displacement. Fuck it, we ball. 49 delta x, delta y, I'll call it delta y, equals, this is gonna be mg delta y plus 1/2 mv squared. Because it starts from 0, so we don't have to worry about the other one. I need something, I need a constraint, I think. It's 2 variables, 2 unknowns. Okay. Unless I can somehow like squish this into something right, which I don't think so. Okay, so we know that it's a spring constant, which is not gonna matter that much. Wait. Oh, it does. Oh. Okay, well, okay, wait, so, sorry. So, in my brain, fs equals 1/2 kx squared, negative, whatever. Wait, is that the force or is that the work? That's the work done. I'm stupid. Is mu k n. That's friction, not... Oh, God. Spring force. What is spring force? It's kx. It's kx. It's kx, I think. I think it's kx? Yes. Oh boy. Okay. So 40. So x equals 49 divided by 40. That's how much we've gone. That's how much we've squished the spring down. So then I can find the energy, and then we can have a beautiful life together. Okay. 1.225. That's how much it goes down. Okay, so it's not this. Get out of here. Okay, so 1/2 kx squared, or so negative, I guess. We're gonna just pretend that the numbers, the signs, are just whatever for right now. So k, so negative 20 times 1.2 times 1.225 squared. Okay, great. So that delta y, we don't know. Is there any way that I can know it? Is there any way that I can not know it, actually? Let me think. Because if we think about it, the way we're putting in work is by this spring, right? And the spring is giving us all of our velocity and our gravitational potential, so it is a split between the gravitational potential and the velocity. So, do we know how much it would split between the gravitational potential and the velocity? Wait, I'm supposed to be not doing dynamics right now. Wait a second. I was not supposed to be doing dynamics right now. We gotta take a detour, chat. What is this? Oh, quiz 1. Okay. We gotta take a detour to work on, where's this thing? This is so sad. Wait, maybe it's not. Wait, maybe it is. What is, huh? I love it when my professor goes, hey guys, an update to a homework problem. The numbers were wrong. And then in another email, like, right after, never mind, the numbers were fine. Okay, wait, he says skip problems 1 and 9. Oh wait, let me see if they're in the practice problems. There's the ones that I want. Yes. Yes. Sickos when they find the problem they want to do. What if my professor did that, I'd explode? It's okay, I didn't do the problem. If I had been a good student, I would have maybe tried it and then... It's okay, see, if you don't do the work, then you can't get mad at the work. Wow, that sucks, sorry. Not being done. Okay. Beer. Big guy. Okay, sorry. Oh god, okay. Find the change in temperature for which the normal stress in the aluminum is negative 11 KSI. I'm so real for that. Yeah, well, I mean, to be fair, I'm doing this quiz that I have to do tomorrow, and this is the problem that's gonna be on it. Or something like this. Okay, so... everything sucks, but that's okay. We have to do some cross sections. Our first one is gonna be on this aluminum. There's a reaction here. Right, so there's gonna be a reaction of A. Let's call this one A, B, C. And so we have to have a force, an internal force, which is, I'll call it that, it's a bar. It's our TAB. It's well, I probably shouldn't call it T, I should probably call it F. I've been doing torques too much. Okay, so we have this one, so our RA equals FAB. And then we have this other dude. This one. It's bad, but that's okay. We've got the same reaction at A and FABC, I believe. Just because there's no extra load. If there was another reaction, we'd have another reaction, but there's no reaction there. Well, actually... there's a reaction here, I lied. Don't worry about it. Wait, no, there wouldn't be a reaction there. No, we're fine, we're fine. Don't worry about it, don't worry about it. Don't worry about it, chat. I wouldn't lead you wrong. I would lead you wrong. Okay, so we have 3 unknowns. That's what we need. We need 3 unknowns. Because if there's only 2 unknowns, we could solve it, but we have 3, which is bad, but that's okay. We're gonna solve it anyway because we're awesome. We're swag and cool, and okay, so we did our equilibrium. It's pretty chill. Our constitution, so the deformation in AB is going to equal FL over PL over EA for AB, plus alpha, whatever that thing is, numbers, letters, same difference. BC is going to be the same thing. There we go. Okay. Now we can start plugging some things in here. So for the deformation at AB, it's going to be this force AB, so that's RA times the length, which is 18 inches, over E, which is in PSI, so that's good, we're in pounds per square inch. 10.6 times 10 to the negative 6 PSI, times our area. Oh, it's lovely, they just give it to us. They just hand it to us on a silver platter. So now we can get a little number out for RA here. 18 divided by... This class is very boring, by the way. Dude, the Pharaoh's Curse. What is it? I don't know what it is. I'm so sorry. I'm so sorry for the cozy tag. I'm gonna cry. For everyone who came to just have a nice mechanics of materials problem, just like mechanics of materials and chill, I'm so sorry. I forgot to add the temperature. God damn it. Okay, don't look at that. Oh, that's gonna really annoy me. That's fine. My whiteboard is a little not white there. It's because I usually work on this because it's like better for my eyes. It's fine. It's fine. It's fine. It's fine. I'm so normal. The mic demon. What's the temperature change? Oh, we're trying to find the temperature change. Lol. Okay. Hi, what are YouTube doing? I'm working on mechanics of materials. So it's about like if you've ever done anything with Young's modulus or like elasticity, it's sort of like the stress and strain that exist in different materials. It's pretty cool. And then I have my alpha here, which is 10. Okay, we're gonna have 2 equations and 2 unknowns, which is good enough for me. So we'll probably just put them into just chuck them into a, whatchamacallit, matrix. I'm just chunking this number in here. Yeah, interesting. Yeah, it's pretty cool. Like you can figure out, one of the really cool problems we did actually, which was maybe the coolest one we did in the class, was, so for some bridges, they are not strong enough, right? Like there's a pre-existing bridge or something, and let's say it's like not strong enough, the materials wise, like it's rusted or something, or it's not seismically up to code. And you would have to like take out the whole bridge and rebuild it, which would be a lot of money. But they figured out that you can actually add a certain polymer that's wrapped around the pre-existing concrete and stuff that makes it stronger. And so the question is how much of this do you need to make the bridge actually strong enough, right? To like have it not twist or have it not break from the force or whatever. And so you can figure that out by doing this kind of analysis, which is really cool, because like we did it and we figured out that you could like reduce the twist of it like by 50% if you only wrap it like 2 times around, which was pretty cool, because it's like you don't have to take an entire bridge down. You can just wrap it with some shrink wrap essentially, and it just makes it strong enough. Pretty awesome, pretty epic actually. This one is also RA. I may be doing this wrong, but that's okay. Oh, I'm so glad I know to calculate out polar moment of area. I don't like doing that calculation. It's 15 times 10 to the 6th times 2.4. It's delta t times... Where did I get that 18 from? Oh, length, 14 times 12. Polymers be like... That's the noise a polymer makes to me. They're like little... I imagine them very like chonky, you know, like they have little... They got like little chonky arms and they're like heh. I feel like it would be like an enemy in like a Kirby game. The polymer. Chicken on screen. Like a little devil. I like circles in my character designs, if you can't tell. Okay, let's see. So what would this be? This would be 12 divided by 15 times 10 to the... Oops, no, not 10 to the... Oh yeah. 2.4. Chicken on screen. It's 10 to the negative 7, RA. Kawaii. Let's see, 14 times 12 times 10 to the negative 6. At some point, this is just a stream of me reading out numbers, and I really appreciate that you guys are still here, even after I just go, okay, well, let me read out the numbers. 1.6 times 10 to the negative 4. Okay, I think I can solve that now. Wait, what does it equal though? Oh wait, we have to do that part. We haven't done that part yet. We have to do the kinematics. So we have these beams, and we have to say that find the change in temperature for which the normal stress in the aluminum is negative 11 KSI. Okay, so what that's saying is that we're gonna have to have some, right? Like we're gonna have to relate these deltas. But we also need to have, so we need to say that the stress, is that the stress? That's the stress, I think. Maybe, I don't know. Don't look at me. The stress in the aluminum, which is AB, is equal to the force over the area. So wait a second. It's equal to, wait a second. Is this really that indeterminate of a problem? This feels not that indeterminate. It feels like they're giving me just like a bunch of stuff. They're giving me negative 11 KSI. Wait a second. Okay, whatever. Negative 11 is the negative is weird a little bit. So that means that 11 KSI, so 11,000 equals, or times area, which is 2.8, equals FAB. Wait, they just gave it to us? Wait, I thought we had to solve for RA. Huh? What? Did I accidentally click on the determinate problems? No, this says that it's indeterminate. Can you explain all of basic physics to me? Oh yeah, sure. Okay. Yes, I can. What would you like first? Is there something, is this just like for fun? Or is this for like, you're like, oh, I'm in a class and like, I'm having trouble with all these things? Because that will change the way that I talk about it. But dynamics is basically physics, so it's a great place to talk about stuff conceptually, actually. This is so weird to me that they just give us this. Because then, what are we trying to find? The temperature change? Oh. Wait, we have the temperature change. Okay, maybe we do need this. Yeah, I need this for a test. Oh, okay. Okay, let me think. While I do this. So, how conceptual versus, I'll go conceptual. If I got enough time. Yeah, I got some time. So I guess at the base level, if I was gonna like start talking about anything in physics or like how you want to approach physics is about balance. That is kind of the key to physics, right? So that could be the idea of balanced forces, right? Like reaction forces. It could be about the balance between relationships of variables, right? Like everything is usually proportional to something else. So that's sort of what you want to keep in mind when you're thinking about physics, is that it's really like looking at something and saying, is this, like where is this in the picture of balance in the universe? And various things have different states of balance, right? So like if we're talking about electrons and they've been given potential energy, they want to balance that out. They want to be at a better state for them. Their better state is at like 0 at rest. So that's what kind of pushes them to do that, right? So they want to find their balance. They want to react equally and oppositely, essentially. So what did you say? You said basics. I'm talking motion, thermodynamics, hydrodynamics, conservation of energy. Hydrodynamics or fluids? Okay, well I can't do hydrodynamics. I can talk a little about fluids. I guess the easiest place to start is probably like kinematics, which is like what you would do with like velocities, right? Velocities and positions and accelerations is kinematics. So Fluids, yeah. So kinematics is sort of the study of solely motion, right? There's no forces involved. You're only looking at accelerations and how that affects your velocity and your position. So at the base level, you have, you know, your position in the world as like an x, right? And then you have a delta x, as in you are moving. Then you have your change in x over your change in time is your velocity, right? How quickly you're going somewhere. And if you do the instantaneous velocity, that's your very, very small change in x over very, very small change in time. And you can kind of figure out how fast you're going at that second. And then acceleration is the change in velocity. So how are we speeding up or are we slowing down, essentially? Generally in kinematics, you'll be working with two types. You'll either have a constant acceleration or a non-constant acceleration. So that would mean that you're consistently speeding up or consistently slowing down, or you're not doing that, right? Or you could have zero acceleration, but that's also a constant acceleration because there's none. And those are where you get your three equations of motion, which are, you know, like your delta v equals at, or your delta x equals vt. You get your 1/2, what is it? It's delta s equals 1/2 vo plus something. These guys. And you're like 2a delta s vf squared minus vo squared, right? These kind of things. Those are constant acceleration equations. You can use those if you have a constant acceleration. But if you don't, then you have to just do some calculus. You'll be given functions probably, or you'll, you know, model those functions. Although those tend to be pretty simple, usually. You might be given, like, say for example, you might be given a acceleration that's like a k theta, right? And so, you know, your integration would be pretty simple. It'd be like 1/2 k theta squared, right? So you'll be given functions to work with that. That's the basics of motion. Then you can like use that motion, right, along with forces, right? If you're talking about forces, we were talking about balance. You always have your sort of grounded equation that sum of your forces equals 0 if you're not moving, or the sum of your forces equals your mass times your acceleration. That's Newton's second law, right? F equals ma. Made an anime about it. Okay. And right, this is just the case where it's your acceleration is 0. Or your mass is 0, but like you're never gonna have 0 mass if you're trying to analyze something. From here, you know, you have to just do statics or sort of force analysis, which is like you'll have a body and you'll have some forces acting on it. Like maybe, you know, there's a force here and there's a force here. Maybe there's like a force here or like a force here. And you'll try and add all these up, right, and see what they equal. And if they equal something, then you'll be able to find an acceleration based off of that. And if they don't equal something, if they equal 0, then, well, you're statics. And you can single out an individual force, right, by doing like vector addition, subtraction, what have you. Right, and this is really where the idea of balance comes in. Because if we have something that's accelerating, right, we know that we have to have unbalanced forces. So if we know that this is going to go this way, then this force here is probably going to be like bigger than the other ones, right? And that's sort of just like conceptually knowing how, or being able to see, I guess, how forces, if a force changes, how that changes the other forces is really, really useful. So like a really good example is if you have like a weight, right, and there's maybe like a tension going up, and then you have an mg, and let's say it's accelerating downward, knowing how, if you change the mass, how that changes how that changes the acceleration, how that would change the tension. That's all really good to be able to sort of visualize. And some people like to visualize it sort of as like energy bars, which also, well, not energy bars, but like, you know, if I have forces in equilibrium, if this one goes up, this one has to go down, right? Like the same amount. Lots of different ways you can do that, but that's always just, I think, a really good skill to have, is to actually be able to kind of like see the relationships or understand the relationships between the forces. Because it'll make your life a lot easier for when you're doing questions like this one, right? Where it's like, all right, so if it's at the top of this thing, like the potential energy is going to be as high as it's going to be, and we have like no spring. Well, if I was doing 3.26, right, we'd have no spring potential energy because that has all been converted to kinetic energy, stuff like that. Not about forces, but I really like the balance explanation. Yeah, I do too, because I feel like physics is a lot about, like, especially when you have, like you mentioned thermodynamics, right? If you have like PV equals nRT, saying like, okay, so if I put the pressure down, but this is the same, volume has to go up to keep the temperature the same. And being able to kind of see that and be more familiar with it on, like, because it's not really a math thing necessarily. It's more intuition. It's more like logical, right? Or let's say like, oh, well, nRT, let's say that V is constant, so we don't have to worry about V. If T goes down, our pressure is also going to go down, right? And like being familiar with the kind of relationships that exist in physical equations, like whenever I would like learn a new physics equation, I always try to do like a mini proof in my brain, right? So like even take like the displacement of a bar in the mechanics and materials that I'm doing, right? It's PL over EA. So as the force increases, our displacement is going to increase, which makes sense, right? Like if we put a bigger force on the end of this bar, it's going to go down more. In the same way that like if our bar lengthens versus is very short, this one is going to deform way more when we put the same force on it. So that also makes sense that it's on the top of that equation. And then as the elasticity goes up, it gets less elastic, which is kind of weird. But as the elasticity goes up, we are gonna, as it gets essentially more elastic, then we're gonna have more of a deformation. And the same thing for the area. If the area gets bigger, we're actually gonna have like less of a deformation, right? So being able to see those and be able to, because like, you know, knowing all of these variables, like it's not like you would ever be asked to prove something, right? Like this, but knowing, if you have a bunch of variables in an equation, like knowing how they change the stuff is really very important, I think, to understanding physics at a deeper level. So you have forces, you have motion, right? And then putting those together, you can also talk about work. So in very simple terms, work is a force exerted over a distance, which gives us a unit of energy, right? So if I have a force over this block and it moves, let's say 1 meter, right? Like how much energy have we put into this block to get it to move? Or an even simpler example, right? If I have a block on the ground and I lift it up to here, how much energy have I given it? Talking about work, there are lots of different ways to find work, and it's kind of a funny, weird little concept because you can have conservative versus non-conservative forces. My professor explained this really well, actually. Gravity is an example of a non-conservative force. We can move this block up and down here as many times as we want, but as long as it goes up here, it doesn't matter, right? Where we did anything in the middle, because it's non-conservative. It only matters the start location and the end location. But if we have a block on a table and there's a friction force acting on it and we slide it around a bunch, we're exerting energy as we slide it around from here to here to here to here. So it doesn't only matter that we ended up here, right? If we moved it straight from here to here versus here to here to here to here to here, we're exerting different amounts of we're giving it different amounts of energy, right? We have to use more energy to overcome that frictional force, because the frictional force is taking away our energy in the form of heat, or, you know, it can take it in the form of like sound or light or whatever else. Not that friction does that, but usually it's heat. The work is just about giving things energy or taking energy from things. I kind of like to think about it as both sides are giving. A lot of the times in electrical engineering, not electrical engineering, electrostatics, you'll no one is safe. No one is ever safe from the mic demon, unfortunately. What else did you say? You said fluids? What is this class? One must imagine Sisyphus happy. I don't even know what there is to do. Fluids, like, I mean, basically the idea is that a fluid is like a bunch of things that is a bunch of little particles, right? And they're all like pushing down. Usually that's what it is. It's usually about pressures, right? Like when you're talking about introductory fluids, which is sort of similar to thermo, except that it's like rho GH, right? So like the deeper you are in the water, the more pressure you'll have exerted on you. I'm trying to think about what I even learned in my fluids classes. I mean, there's like Torricelli's and like Bernoulli's equations, which are like, if you have a fluid that's going through a pipe and it goes into a bigger pipe, it's going to be slower, I think. I want to say it's slower. What else? Thermo's fun too, right? If you have a bunch of particles. I mean, the idea about like thermo is like you really do just kind of look at individual particles and you say, okay, well, the big things to know are like pressure is based on force, right? So a couple cases that might make pressure increase is if your molecules are moving faster, which means that they're hotter, so that has to deal with temperature. Or if they have more collisions, which has to do with volume, right? So if you are making your container smaller, your particles are going to be hitting the walls more often, so they're going to have a higher pressure. Or you can just have them move faster, and then that's going to give them more energy, and then when they collide, conservation of momentum, conservation of energy stuff, they're gonna exert more force on the wall. What else? Temperature is like the average. It's basically just speed when you're talking about thermo, like average kinetic energy of a particle, right? The only types of energy that you can have, actually, like technically, is like a velocity. You can have potential energy, but it's not really real energy, right? It's just kind of the idea that you're going to do something sometime soon. And then volume is, I feel like, more self-explanatory, right? Like, if your volume gets bigger, it's not going to affect your temperature necessarily, because you aren't, like, changing the speed of your particles, but it is going to affect the pressure. If you have a bigger volume, you're going to have less pressure. I think you said conservation of energy. I feel like conservation of energy is actually not super tough. All the fundamental stuff. That's crazy. That's like a lot of stuff. I had my first semester of physics was like, it was mechanics only. But then again, I had to take 3 physics. But it was also first quarter physics, so semester quarter is a little different. What was I gonna say? I was gonna say Oh, conservation of energy. Essentially, the idea is that like energy can't be destroyed, ever, right? It's always going to go somewhere, right? So that means that if you have like a block and it's moving and it's going to go over a rough surface, we have, you know, energy that's lost as it slows down, which is going out into the environment as heat, right? So it's kind of just saying like conservation of energy or conservation of momentum is just like taking all of the momentum, taking all of the energy and just kind of accounting for it, right? So like all the energy you have at the start equals all the energy you have at the end, which is exactly what I was doing with this, right? So we say like the gravitational energy at the start plus the spring potential at the start plus any work that we do plus the initial kinetic energy at the start has to equal the final kinetic energy plus the final gravitational plus the final elastic potential. That's pretty much physics. I mean, to be honest, that's pretty much everything you could think about. And the fun thing is like usually when you do fluid or thermo or any of that kind of stuff, like all of it still has the other things applied to it because they're just really little things that all these physics are acting on, and then because they're moving in this bigger system, they have other properties, right? But when it comes down to it, really everything is just a particle, and it's all particle physics. So that's like your kinematics, your work, your forces, all that kind of good stuff. There's this one, okay. This is wrong. This one. Okay, so the change in them have to be equal, actually because of, not really because of conservation of energy, but more because of, it's a constraint that we have. Like your bar can't break through the wall in this problem. So we know that this plus this is gonna equal this. Oh, we do, it is indeterminate. Okay. So, oh god, I don't want to have to do this. Okay, 6.065 plus 3.33, 9. Okay, so 9.395 times 10 to the negative 7th RA, which we can solve for. Plus, I really hope this is right. It would really make my day if it was right. It'd be lovely to get a dub. I so often take L's. Okay, equals 0.02. And then we have 30800 equals RA. At bats. Thanks, Damie. That was actually pretty insightful. Aw, thank you. I'm glad it helped. If you have any questions, feel free to ask. There's a chance if it's particularly fluids I have not done in 2 years. So been a while for that one, but other than that, I do know some things. Times 10 to the negative 7th. Oops. This times 3.0. Alright, so 0.041. I really hope this is right. This is like a very small temperature difference, but I mean it's 0.02 inches, so like... actually... okay. I got a negative number. That's not a good sign. It's actually a bad sign. Where did I go wrong? What did I do wrong? I have no clue. I don't know. What? I don't know. Yeah, this is way too small. Why is it so oh, because it's 10 to the negative 4th. Okay, well, so it doesn't fix the negative number, but this is 10 to the negative 4th, so that makes my life a lot better. Okay, what if I just pretend that there's no negative number there? That's crazy that there's a why would there be a negative number there? There really shouldn't be. Okay, well, whatever. We'll figure it out. This times 10 to the 4th, please? Okay, 22.26. I'm just gonna get rid of this. Get out of here. I like 22.26. It's gonna be wrong. I'm calling it. It's gonna be wrong. Let's see. There's a worked out answer though. Please, please, please. Okay, it's very wrong. It's very wrong. It's very wrong. Uh-oh. Wait, what? Wait, what? Why did he solve it like this? Wait, what? Okay, he just like didn't solve. This is crazy. Wait, this is so crazy. Take a look at this. Take a look at this, guys. You're never gonna believe this. Look at this. He didn't solve anything. Just solve PAPB-R. Well, I guess R. Wait, where's R? Where's he getting R from? Huh? I mean, so I'm getting the same thing. Wait, it's negative R though. Wait, why is he saying negative R for both of them? Kinematics, okay, I got that part right. I don't really know any of the work that he did though. That's crazy, dude. Wait, do I need to like click on it maybe? Nope. That's all I got. Okay, wait, there's a video solution.
Back with another problem.
Okay, sorry. No, okay, never mind. There's the video solution is also bad. Well, that's depressing. It's okay. I guess. I could have just, I guess, done something wrong. I just check my he could have given any intro. I could have given any intro steps or intermediate steps. That would have been awesome. Okay, well I got some point. I think I would get like a 7 out of 8, but I want to like get it right. The setup is not incorrect, and actually the equation isn't incorrect either. I would have to do a different thing. I would have to do 2 equilibriums if I wanted to have 2 reaction forces up there. Because I would have to say then like, oh, overall equilibrium RA minus RB equals 0, and then I could basically plug in to have this happen. What is up with this? Okay, maybe I just crunch numbers again? What do we think? Times not plus, what am I doing? Times 2.8, there we go. Okay. That was how you're supposed to check your answer? Cause that's crap. It's okay. It's normally they're a little bit better than that. I don't know about that one though. That one was not great. Hey, I mean, it's just kind of like when it's in the back of the book, you know? Just solve. Yeah. Well, because, I mean, to be fair, it is just like punching a bunch of numbers in. But I don't know where I punched the numbers in wrong, which is why it's hard. Okay, so I add these together. That's our RA, and this times 30800. Yeah, because I already get like a wrong answer. when I do just this part. What? For reference, I guess, because it would be hard to tell where I'm going wrong. Essentially, what's happening is that I'm calculating a deformation based off of the reactions, right? So these are gonna deform a certain amount because there's forces on them, because like of their length. And I'm basically calculating a number that's larger than this gap. Really great too when they forget to update the back of the book answers to selected problems. Oh my god, that's the worst. That's the worst. I can't tell you how many times I've just like, how do I say this without like being struck down by I think it's a really good idea to look things up in whatever way you need to look things up. It's gonna be is my answer. Because if you can do it and you can learn from it, 100 million times better than just floundering. So if you get to like a point like this, right, where like you've done it and you actually like know that you have the theory right, but like your answers are wrong, like your answer is wrong somewhere, Google that shit. Figure it out. Talk to a classmate. Maybe my T's are incorrect. I don't know if my T's can't be incorrect. I lied. You know how many mistakes they make in these textbooks? Well, the funny thing is like this it's not a textbook answer because it's by professors like doing it out, but they're also like 15 years old, some of these solutions. So not my professors aren't 15 years old. Oh wait. No, wait, I got rid of the negative. I was supposed to say maybe it's just negative, and then I add it? Wait, maybe I add it. Wait, maybe I add it. Oh, wait, shit, maybe I add it. Wait, what would that do for me? If this was negative, that means this would be negative. That means that I would add it, I guess? This plus 0.02. This divided by... Wait, I might be cooking. 0.14. Swear to God, if this is it, I'm gonna cry. What? Oh, I didn't divide it. Oops. I multiplied it. 121.9? No, fine. That's what it... Wait, it's like... that's like kind of close. Not that close? I don't know why it's not that close. I think the methodology with correcting, updating the solutions is to pay some grad student to do it. Can they pay me to do it? I wish I could do that. I just deleted the entire layer. That's how it's going. That's how it's going. It's right. If I just add them. Sure. I was like 121, 122. That's like close enough. They probably rounded somewhere. Let's be real. Where would they have rounded? I don't know. Anywhere. That's crazy. That's close enough, though. Wait, so okay, the reason why is because our stress was negative. That means our force is gonna be negative? That doesn't make any sense. Sure. Ooh, Fahrenheit, yucky. Yeah, America. We also got kips per square inch. Kip is 1,000 pounds. We haven't gotten into slugs. But you know. You could say that it's in slugs. It's in slug. Taking my brain a second. No. I was gonna say 32.2, that's pounds mass. Slug is just 1, isn't it? I think it's 1 pound force per feet second squared. I don't know. Okay. Well, that's like close enough. Whole Imperial System units look like the Tree of Life thing in the intro to EVA. There's some things that are interesting about it. Like, I think the idea... One of my professors explained to me, he was like, oh, it's cool because it's divisible by 2, 3, and 4. Which are all good things to be divisible by. But like a foot, right? 12. Like, it's based off of 12s. But like, 5 and 2, I feel like, is the better pick. Why would you want 2, 3, and 4? Okay, I might do one more of these. Just because I haven't done them. Axial indeterminate. He's definitely going to give something like this one that I just did, but this one might also be kind of close. Very similar. Oh god, it's huge. My bad. This blows up the world because it's too big. Okay. Another. Okay, the subject is decrease. Decrease. A 7 kilonewton load. Here, look, we got newtons and meters. Kip is 1,000 pounds. Yep, it's 1,000 pounds force. 1 kip. Really funny. And applied displacement at the support at C. Rounded to the nearest newton. Okay. Well, I guess the fastest way to do this would be, well, so we know that, ooh, there's an applied displacement that actually displaces. God bless America. I guess we just start with some, what's the problem? It's this problem. This is the problem. It's a bar subjected to a uniform temperature decrease. So it's an indeterminate problem, which means that we're gonna have some extra forces that we don't know about, and we're gonna have to solve for those. I'm gonna start by doing a first free body diagram of AB. So there's a reaction here, which means that the internal force is gonna go this way. So FAB equals the reaction. And then we can do our other one too. It's a little silly, a little goofy, but don't worry about it. Don't worry about it. It honestly feels like, okay, I'm not gonna lie, it feels like these problems, when you only have one reaction, they're kind of a gimme, because they like feel like they're not indeterminate, but they are, but like, I don't know. And then we have our, oh no, we have a 7 kilonewton load is here as well. That's like an external one, and then our internal one will be FBC. So FBC, I guess I should probably put it in terms of RA, huh? Nah, we're fine. It's fine. It's fine. Okay, FBC equals, or plus 7 kilonewtons. We'll do my due diligence equals RA. I kind of don't like writing it like this. I would rather write it like, well, I guess that's actually not too bad. I guess I would rather write it minus RA equals 0. Picture isn't even a scale, SMH. Oh my god, nothing is ever to scale. It's kind of to oh wait, no it's not. 200 millimeters. Kind of to scale. Wait, that's really funny, yeah. Why did they do that? Normally they're more to scale than that. That's kind of goofy. What is a KV? What are we seeing KV? Oh, KN? Was it cut off? A kilonewton is a KN. So we're in metric. Everybody's favorite friend, the metric system. Oh, it's KN, yeah. Oh, was it cut off like right there? It'd be like kilovolts, I guess, if it was KV. We're not doing electrical engineering, don't worry about that. Okay, so we got some equations, we got 3 unknowns, we love that, whatever. It's fine. I shouldn't say whatever. Okay. The displacement of AB. They actually tell us that there's some extra displacement at UC, I guess. But we'll figure that out. Wait, an applied displacement. Oh, that's weird. We'll have to add that to that, I guess. That's kind of, oh, that's kind of, okay, whatever, fine. Okay, so we're gonna have PL over EA plus our temperature difference for AB. And then for C, BC, this is gonna be PL over EA plus our temperature difference plus the 0.02. Because that's just, I guess, we just apply a force that gives us that. But instead of giving us a force, they just give us that. Okay. Now this is in millimeters, so we do have to be a little careful when we're writing out our plugging in stuff. So we're gonna put everything in terms of RA for now. So RA for FAB, right? We put in that, and then the length of that, which is 300 millimeters. I'm gonna instantly divide this by 1,000. So you get into meters. No way that we're not. Then we got 200 gigapascals, so it's 200 times 10 to the 9th pascals. We like that. We like pascals. And then we've got area in millimeters, of course, because... Well, okay. I mean, the reason why it's in millimeters is because... Oops. 200, 1,000 squared. Yeah. The reason why it has to be so small is because to have the model that we currently have for this, to have all this stuff work out very nice with the algebra, instead of doing a bunch of linear algebra, is that we have to assume that it's very, very, very long, proportional to its cross-sectional area. So we gotta have these tiny little millimeter guys. And then we have -12. Okay, so here's the thing. We're pulling outward, but we're shrinking it. How old am I? I'm 20. We're pulling outward, but we're shrinking it at the same time. So that's gonna actually be a -12. And then our length again, so that's 300 divided by 1,000. Okay. Oh no, you've collected my data. Okay. And then this one is the same thing. And we're gonna... Okay, the question of the kinematics for this is gonna be a little weird, but we'll get there later. Okay, so RA is actually, we're gonna do FBC equals RA minus 7 kilonewtons. Give your address. I joke, I funny joke. Average Twitch streamer. Okay, do I want it in kilonewtons? I don't want it in kilonewtons. I'll just 7,000 newtons. Times, what do we got? 120 millimeters. Over 180. 80 times 10 to... There's a lot of numbers. Lots of numbers here. I don't enjoy... This is the part I don't enjoy because, like, oh god. There's so many numbers, and none of them are really that important. It's okay. We'll get through it. I'll live. Plus -12. So, okay. For C... Yeah, it's the same thing. Except not 300. This is 120. And I don't believe it's 12. It's 21. Yeah. Then plus 0.02. Too hard for me? Oh yeah. Don't worry about it. They're static, dynamic? Oh yeah, I just need to do this and then I was gonna go back to dynamics. Unfortunately, the dynamics is not any easier than this. This is just like, this is like grunt work, but dynamics is like, oh god, I have to think and my brain hurts now. Okay, before I just start joyously plugging numbers in, let's figure out what the kinematics for this is gonna be. Okay, so we have to figure out the reaction at A. I guess we kind of need to figure out if... Okay. We're gonna assume that it's 0. Is that true? Do I know the spectral theorem? Ooh, no, I don't know the spectral theorem. Wait, let me see. Spectral theorem. Wait, maybe I do actually. I think it's diagonalized. Is a result about... Oh, I don't know about it, but I do know about this, that kind of thing. I would love to hear about it if you'd like to talk about it. Or do you have a question about it? If you have a question about it, I probably can't answer it. I definitely can't answer it. I kind of gotta assume that we set it to 0.02 millimeters, but I don't know. Because if I set it equal to that, then this is just gonna cancel out the 0.02s. It's either I set it to this or I set it to 0. If M is symmetric, it's diagonalizable. I think I may have heard that before. So powerful. That's so cool. Oh, I miss linear algebra so much. I try to use it as much as I can, but my classes are not like, they're too boring. They don't use it. They just, I mean, I use it to like solve matrices, like systems of equations and stuff, but like, sighs so sadly. Okay, let me start doing some groundwork. Wouldn't it be easy to transform the equation with all the symbols and then plug numbers in, or nay? Yes, except for the fact that like this is just r plus some constant, and so whenever I have like, if I had a bunch of stuff in here and it was an issue, I would transform it. But because like basically everything is getting out of here except for this, then I kind of just leave it like this, because I like to do my how do I describe it? It's like I like to do my math in like chunks. I'll rather question, what is 40 divided by 3? Great question. Definitely not putting it into a calculator. 13.3333. I knew that off the top of my head. I'm so cool. I totally knew that one. Come here because you know a guy who can do numbers well, for sure. What is 2? More than 1. Or maybe not. Some people disagree on that one, actually. Okay, 12 times 3 times 12. They can't make these problems nice ever. They have to make them awful. So it's so goofy. Okay. Let's see. And 120 is like annoying too. It'll be 0.12, I think. Yeah. Oh god. Okay. So this one is a little more annoying. So 0.12. I'm gonna do it for R first. The successor of 1. 0.12 divided by 180 times 10 to the 9th. And then I can just multiply this by the other thing. Times... Okay, that, and then 5.5556. I didn't need that many 5s. Minus... We've gotten to the quiet part of the stream. ASMR, Damie reads you numbers off of a calculator. Of course, they couldn't make this one the same either, because they hate me. Okay. Do I mod? I don't know. I've never gotten diagnosed. I'm a weird little guy. I can say that for sure. I can say that one for sure. 0.12 times... That's not the first time somebody's asked me that question. Except that was less off-putting than the other time. 2-1 times... There we go. Equals 0. I will have that power in 10 years. Rev's unlocking DLC right now. I can't figure it out. That's so funny. Okay, this sucks. I'm sorry. This is the worst. Look at this thing. God, okay. You know, I'm a big proponent of like all numbers are beautiful. This is a lot to look at. 5.55. Power of autism. No, of being a psychiatrist. 13.0556. Oh, yeah. Once Rev gets a master's degree. I still can't believe you're getting a master's. That's so cool. That's so swag, even. Oh wait, this equals this. Okay, we're getting there. There's a number. There's a number hidden in here. In the depths of hell. Okay, here we go. Do an epic damie diagnosis stream. I was gonna say that, and then I was like, I shouldn't say that. The specialist event of the year. Okay, we're getting it into a power of 4. This is okay with HIPAA. Don't worry. Rev, this is the first stream that Rev ever does and instantly gets banned. But not by Twitch, just banned from the practice of being a psychiatrist. Okay, I got a number. It's a good number. Was I even trying to find the reaction? I think I was. 5.625. Oh, kips. Whoops, that's kilonewtons. 5.625 newtons. 5625 newtons. I said that a lot. Okay. If this is wrong, I am gonna cry. But that's okay. It's not that hard. I don't know why. Okay, it's not right. It's not right. God damn it. My license taken away the day after I get it. Okay, guys, I did it for the bit. UAB plus UBC equals negative. Oh. Okay, wait, are the temperature changes negative? It looks like they're positive. Why would they be positive, gamers? Why are we... Okay, they're negative. They added them negative after. Oh, they probably put them in with the T. Okay, so the only thing I did was I messed up the negative 0.02. And I shouldn't add the deformation in there. So basically I just... It's this. And this. Oh, okay, it's not that. Look, I can wait a second, look at this. Wee. Okay. Sorry. Okay, oh fuck, god damn it, I didn't mean to hit that, I meant to hit this. I don't know why I keep getting that. There we go. Negative. That little guy ruined my life. Right there. Okay, he didn't ruin my life. It's pretty close. Alright, let's do dynamics. I don't want to do this anymore. Board streamer. This one is gonna make my head explode. I don't really know if the other ones are gonna be any better though, because I already said the other one that I was trying to... Wait a second. There's 2 random conceptual questions in here. What the hell? Okay, I don't want to do that. I want to do the big chonky boys. Oh, this looks awesome. Not being sarcastic at all. Everybody loves thin circular rods supported in a vertical plane. Okay, vertical plane. There's weight. God damn it, this looks really fun. Okay. Okay. We got a bracket. Attach the bracket and loosely wound around the rod is a spring of constant pounds per foot, an undeformed arc length equal to the arc of circle AB. Okay, cool. Oh no, that's gonna be awful. An 8 ounce. What's this, like a baking recipe? How much is it? 8 ounces? What? 2 pounds force? 1 ounce force? Are you kidding me? There's an ounce force? Bro, what? I did not know this was a thing. Okay, it's a 1/16 of a pound force. That's... Who came up with that? Okay, 8 ounces, so it's 8/16, so it's 1/2. Why did they not just say 0. Okay, mass C equals 0. Thank you for the Pinos. 0.5 pounds force. Wait, pounds, yeah, pounds force. Okay, wait. Yeah, yeah. Can slide without friction along the rod. Well, that's great. Oh my god, okay, knowing... Oh boy. Okay, guys. The smallest value of theta, for which the collar will pass through D and reach point A. Okay. Let's quantify what that means. What do we have to find? Okay. So for A, we know that like the distance it has to travel needs to be 2 pi r. So that's gonna be, now do I want to keep everything in feet or in inches? I think I want to keep everything in inches, so we're gonna make the choice to keep everything in inches. So this would be 24 pi inches. That's how far it needs to travel. Okay, how is it traveling this far? Well, it's gonna have some spring force. Okay, let's write out this. So we have a V, or I guess like a T0. T0, this is gonna be 0. Doesn't have any kinetic energy at the start. It's gonna have some initial gravitational potential, which will come from theta. It's gonna have some spring potential, elastic potential, and then it's gonna have some work done to it potentially. Sorry. It was VGF plus VEF. Okay, I don't know why I made them bigger on that side. All right. Well, let's define a datum. That's another good place to start, right? We'll say this is the datum. Okay, well, we know that VGI is gonna give it some, it's gonna have some height because of theta, right? So the height here is gonna be, I guess this value, which would be, okay. It would be 12 inches, the radius, minus cosine theta. Okay, that's good. We got that. That's a good start. Our spring is going to be stretched a certain amount, which we can. Okay, this is also good. This is also good. So VEI is going to be -1 or 1/2. K, and then so our unstretched spring is going to be 6 pi length. That's how I feel. I feel like Damie Kipo. My god, when I do these problems. Plus, no, minus. Yeah, minus the arc length, so theta times 12. I'm like stepping on eggshells here, I think that's right. Damie Pino. New emote. Damie Pino. No, I love Pino. I love the Pino emote so much, I don't know why. He's just a little guy. Wait, let me just check one thing real quick. Who's pinging me? Is this? Sorry, someone's sending me our website. Not my website, a website for a thing. Whatever, it's fine. Don't worry about it. Okay, are there any applied forces or are there any friction? Not the correct tense of that word, but no, there isn't actually any of those things. So we don't know what this is. Well, I mean, I guess we don't know what that is. We're trying to find a value of theta, so like we'll probably have to do some kinematics or some garbage to figure that out. Yeah, we will. Our gravitational potential, this is great, we can do that. I'll put it here. Equals, right, mg times 12 inches. Love that. And then we know that our VEI is going to equal 1/2 k times 6 pi minus, there's going to be a big number. Wait, is that true? Wait, this is not correct. It's just this. Yeah, because that's how much we're changing it. Okay. And this one we're changing it 3 times. Don't look at this. 18 pi. I think. I think guys don't. Okay, so the only thing we don't know is TF, but we can find the VF based off of kinematics? Not really. Not really. I lied. How do I get rid of TF? Oh no, transformation, TF. Okay, I shouldn't say that. This is so close, we're so close. Next thing, thread join. Running over to Google, kicking my feet, and jumping around like a funny little lad. Okay, thread join. Okay, this looks great. I don't know if this is Java. I don't know if you're doing Java though. Are you using like C++ or no? You're like Linux or something. Thread join. A zombie thread? What? I don't know what this is. How do you start, join multiple threads to speed up operation? Oh, I have no idea. That's like a complicated question. I would maybe check out that. That's for like the easy one. To speed up operation? Oh, I don't know. I have never done any optimization thing. I literally said to myself, I said, Damie, you work in computer science. You're not working in optimization. I went, okay, that's fair. And then I didn't work in computer science either. Speaking of computer science, I could do my MATLAB lab. Okay, wait, so TF. Is there a way that I can just like figure it out? Oh wait, maybe because it's a circle? If I know the velocity. No, I can't do that. Because like, it's angular velocity, whatever. That's not gonna... We're probably gonna have to do that for B. The value, it will pass through D and reach P. There's gotta be something, there's a link I'm missing. I feel like I'm in Blue's Clues, but I can't find the clue. What part am I missing? What could possibly give me anything about? So this is equal to 1/2 mv squared, vf squared. For which it will Okay, if it just passes through D, maybe we just say the V final is 0? Right? Because like the minimum value, min value, V equals 0 at A. Okay, I don't hate that. That seems good. I'm gonna say it's 0. Whoop-de-doo. Okay, now I just have to solve this thing. This is not a fun solve. I think I might need to graph this one, I'm not gonna lie. There's a cosine theta and a theta added together. I think we might need to be doing a little bit of graphing. Fun times, chat. Okay, M. Oh yeah, 0.5. Wait, no, wait, MG is 0.5. Oh wait, these are also gonna cancel. 0.5 cosine theta. Plus K is 3 pound-foot. Pounds per inches? So 3/12ths. 3/24ths. Times 12. Oh god, there's too many numbers here. I'm gonna do that out. Okay. So we have 1 over 12, 1 over 2 times 3 over 1 times 1 over 12 times 12 theta. So cross, and that equals, this one goes away because I already did that one. 1/2 3 divided by 12 times 18. Oh, this is not great. Okay. So this is what? This is 6. And that's 9. I gotta do it out anyway. Okay, so 0.5 cosine theta plus 3/2. Why did I just type 3/2 into a calculator? 1.5 equals, now this one, that's 1/4, 1/8. 18 divided by 8. Just make sure. 2.25, okay. Alright, let's see. Time to graph theta. Okay, let's all go on a journey together, actually. To beautiful land of Desmos.com. Browser. Desmos. Okay. So what do we have? Going on a field trip. Okay, 0.5 cosine x plus 1.5x equals, we got one line. If I zoom in far enough, it'll give me an answer. 4.712. I just opened Spotify. 4.712 radians? 4.712 radians. Is that correct? I don't know. I don't know if that's correct at all. Let's see. Does it make sense in any sense of the word? 1/2 times 360 divided by 2 pi. I don't think that's correct. Funny story. Yeah, I got 269. That would be above A for sure. What is this supposed to be? Oh no, I'm like, this is so scuffed. It's supposed to be 43.5. Okay, wait a second. But what if I subtract 180 from this? What if I okay, no. I'm I'm doing something wrong. What am I doing wrong? Wait, kx squared. Okay. This is gonna make Desmos like actually hate me. I don't know if it's gonna be able to graph this. I think it will be. Okay. That's this. What's 1.5 times 12? 18. I didn't need to even click that. Okay. Okay, guys, we're going back to Desmos. Oh, that's the problem. Look, you can see it. Okay, so 18 x squared. Oh? Oh? Wait, we might be onto something here. Let me cook. Okay. 0.6082. Zero 0.6082. On my heart is in my throat. 34.8. Why is this so close but not close? Wait, did I multiply gravity in here anywhere? Not really, right? Because I got rid of the MGs. Yeah. Why is that like weirdly close? 34.8? Oh, whoops. Not there anymore. 34.8. This is so weird. What? What could I possibly have done wrong is the thing. Maybe I like forgot. Okay, I could have forgotten like a little thing somewhere. This is supposed to be F. Oh. Huh, yeah, maybe that would do it. Yeah, maybe that would do it. I don't really need to do the times pi squared. 5.0625. This is gonna get it like completely wrong. Okay, 5.0625 pi squared. Back to Desmos. We're just going on a lot of field trips today. 5.0625 pi squared. Uh-oh. It's really out there. 1.667. Thank you for Metal Bite. $95. God damn it, we're back to where we started, at being bigger than 90 degrees, which is not correct. What are we doing wrong? What are we doing wrong, chat? What are we doing wrong? Oh god. Maybe my like spring force is like not correct. Wait, does it like leave the spring or something? Oh, wait. Not attached to the spring. Wait. Not attached to the spring. Oh, okay. So, funny story. There's none here. God damn it. I'll stick to chemistry, thank you very much. There's none here, there's none here, always none, and then 0 here. Damie's attached to the spring, I fear I am. My brain is on this spring. I was like, how is the spring letting it go all the way around here? Okay, bye, need sleep. Have a nice 7 night sleep. Thanks for hanging out. Oh my god. Oh my god. Okay. Maybe this will work. Maybe the gods will bless me. Well, 0. Please, 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 please. Uh-oh. Wait, it's just not anywhere. Wait, it's literally not showing up anywhere. Where is it? Wait, what? Wait, what? What? Where did it go? It's not here. Hello? What? What? Where did it go? It needs to come back. Now it's gone. I don't even have any solutions. Oh no. Well, I mean, I guess it kind of makes sense that, like... Wait, no. I feel like that could be something that exists. Wait, why is it not showing any solutions? That's really weird. What if I just said it equals nothing? Oh. It never equals 0. Did I get a thing wrong? Does it need to, like... Wait, what if I said, like, negative? Then that would be 1 point... Okay, wait a second. We might be onto something. Every time I've said that, I've been wrong. What? 9 point... What? Huh? That's weird. Okay, so no, we're not onto something. I don't know what's up. I don't know what that is. I feel like I don't know what to do. Maybe it was just like maybe like that one time I did it was correct. Well, no. It says it's not attached to the spring. Oh, hey. Hello. How's it going? Cruise. I don't know. What the heck? I feel like the V... Oh, it definitely has to be 0 at A, because that's like the minimum it can be. Right, because what else could it be? Or maybe not, because it would be falling down from D to A. And there'd be gravity accelerating it, so maybe it wouldn't be 0. But I don't know how you would do that. Can you help me with mu static? Oh yeah, sure. Static friction? Wrong one. There we go. What's up with your static friction? Maybe we can figure it out. Maybe I can figure out more than this, or maybe I can't. Who knows? It's the beautiful world of beautiful worlds. Maybe I can do I'll do a conceptual question, maybe. Yeah. This one will be easy. Maybe I shouldn't say that. Oh boy, okay. M equals 20 kilograms, mu static equals 0.5. And the force on the object is that. What time does the object start moving? Wait, the force on the object is... Oh, I see. Oh, okay. So you want to find... So first off, like, when you think about friction, your static friction is sort of like a limit, right? So the idea is that you can load up something with a bunch of... So like if let's say your static friction, I'm going to do it sort of symbolically. Like let's say your load, like your fx max, right, can be 3 arrows. So here we have like, you know, the static friction that, and then when we add this, then it's like the point for it to start overcoming that static friction and then having the, you know, the friction, the kinetic friction working against it. So your first step would be to find the maximum static friction, right? So your Fs equals mu sub n. So you want to draw like a free body diagram and you want to find that normal force, which depending on like, I don't know if it's on an incline or something. But you have that. And you'll be able to get like a number for that. So you'll have like, you know, x, right? Then you want to figure out, okay, so if this is my force and we have a force equals 8t squared, when does that equal this? Right? And if you have a force at a direction, your friction is going to be acting in this direction, right? So any force up here isn't gonna matter, right? Because that's going up in this direction. So you only want to do the equilibrium in this direction when you're doing your applied forces. So you just have to figure out what this is based off of, well, so actually because it's an upward component, you'll have to add this into your, you'll do Fy equals 0, or Fy equals may. It's not accelerating upward, so we have 0. Which if you're in a statics class, you know, doesn't matter, whatever. But you're in, it says what time does it start moving, so maybe. So this is going to be n plus f applied. This is the up direction, so that's going to be sine, right? Sine theta equals mg. And so then you want to solve for n, and you get mg minus f applied sine theta. And then you can say fs equals mu sub n. Which is mu sub mg minus f applied sine theta. Sorry, I'm writing very fast. And yeah, and then you can just say like when your fs, when your f, so it would be like 8t squared cosine theta equals mu mg minus f applied. And these should all be numbers that you have. So you just solve that. N equals 4.8t, yeah, and then you just have to keep trucking along with the numbers. So this would be 8t over here, right? We know what f applied is. That's 8t squared. I would graph this, yeah. Because you have your u equals mg term, so you're not going to be able to really solve it with a tangent or anything. Pull that out of there. Okay, let's see. 2 small balls. Okay, it's funny. I love small balls. With masses 2m and m are respectively released from height h above the ground, neglecting air resistance, which is the following statements are true when the 2 balls hit the ground. Okay, well, if we start off with TO. Okay, well, let's do our little equation. So delta VG, I'm not even gonna add, so delta, oh, whatever, fine. I'll delta VE plus N. Okay, we don't have any friction or applied forces. So we know that T, or so, let's do this one. So mg, let's do the 2m, to 2m g equals, T0 is going to be 0, TF, basically. And the other one is going to be mg equals TF. So it's not, I think this question is mostly about like the velocity, right? Like, oh, is it, the velocity is squared, but this isn't about velocity, this is about kinetic energy. So it's just directly proportional. The kinetic energy of A is twice the energy of B. They're not the same because they have different masses. Cool, I'm gonna do this one last conceptual one, and then I think I'm gonna take a little break. I think I gotta look up what I'm doing wrong on one of those, because I think it's consistent enough that I think that it's some issue that is plaguing me. But to be fair, like, I haven't had a second lecture on it, and we only just started doing work and energy, so it's not really like an issue, a skill issue. All right, block A is released from rest and slides down the frictionless ramp to the loop. The maximum height of the loop is the same as the initial height of the block. Will it completely make it around the loop without losing contact with the track? Okay, this is a classic question. All right, so as we go down, we have like all, so let's say that like this is our datum. So down here, we have 0 potential, all K. Up here, we have 0 KE, all potential. Right? I've done this question before. I think there's something about, because if you don't have a velocity, oh, I don't, it's like a, we might have to do a free body diagram. So like over here, or like when the block is like here even. So you have mg going this way. Actually, no, this is work and energy, so I might need to do that. Let's see. When I need to find the time, I get weird thing. I do f max is less than or equal to ft and get 4.22. Let's see. Well, I didn't delete that, so I can pull this back up. We can actually just graph this. So in this case, we're trying to find the second right where it slips. So you're gonna set it equal to that. But yeah, it shouldn't matter. Let's see. What did you say mu was? 20 kilograms per, okay. I'm gonna pop over to my graphing here. 8t squared cosine theta, which you said cos theta is a 0.8. Equals mu, which was 0.5 times 20 times 9.8 minus 8x squared. I'm gonna change it to x real quick. Sparkle on! Oh my god, I'm sparkling. Sparkling for the sparkle gods. Sorry, wait a second. Sine would be 0.6. Okay. Oh, what? That's also not 5. Why? What the heck? N equals, let me see. Where's the object? It should be right. I mean, I'm not accelerating the upward direction. Fs equals... Oh. Wait. No, yeah. Because we do, so this is our equilibrium in... So this is our equilibrium in this direction. And then if I were to do this, like, and not be silly about it, let's be more real about it. So if we do fx equals 0, then we say F applied. I'll write it in. Cosine theta. Minus n equals 0. That should be it, unless there's an acceleration thing. Chicken on screen? Wait, why did it... Oh, does it not redeem at the same time? I mean, I can give you a free chicken on screen. It's so sad, it doesn't redeem at the same time. I want to be sparkly and chickens. I like... Maybe there's a cooldown or something? I don't know, that's so weird. This is also weird, because I feel like this should be right. Oh wait, sorry, not N, this is FS. But that's okay, because that's music S. Oh, there's chickens. Did I get the numbers wrong? Are we sure the sines and cosines are correct? Because I don't really know. Huh. Well, that's certainly like a start of the way there. I don't know if the numbers are clearly not working out, but... Yeah. Sorry, I can't take you all the way there. I can see the problem. That might be a little easier too, but... Oh god, this question is like awful. I dislike this question. Okay. I mean, the answer that I think you can't give is like, well, the energy is the same at the top, so it's gonna make it around. It's not that easy. So we gain kinetic energy. As we go up, we lose the kinetic energy. Now the question is I think you need a certain amount of energy, but it's like a force thing, you know, like to keep accelerating, because you literally will have 0 as you go here. This is 0 equals t. mgh equals p. And you have your mg going down here. And you have your normal force down here. I lied. Has to go up, doesn't it? Wait. No, your acceleration can go... I'm not sure. I think it goes like this. That doesn't make much sense, does it? I don't know. In my brain, I feel, without losing contact. If I shake it, maybe it'll tell me the answer. Start beating up math problems in the back alleyway. Why are there so many of these problems? Oh god, there's still more. Okay. Yeah, I think I might have to... Wait, when is this due? Okay, it's due on Friday, so we're actually chilling. I'm guessing I'll probably be better at it after tomorrow, but... Yeah, I don't know if I can do this one either. This one, oh, I started doing this one. I don't know if you guys probably didn't see that one. This one too. What if I just like sink my teeth into all of them is the thing. That could be kind of fun, because then I could be like, ah, well, yeah, I see where I did this, and then I could like go off of it when I actually like learn how to do it better. That'd be nice. Let's see. I'll just take a look at this one. God, okay. A spring is used to stop a 50 kilogram package, which is moving down a 20-degree incline. It has spring constant of stuff. It's initially held by cables so that it's compressed 15 millimeters. Knowing that the velocity of the package is 2 meters, when it's 8 meters from the spring. Okay, that's a crazy thing to say. Well, here's our state 1. Well, I don't actually even know if that's our state 1. When do we think about state 1 being? Well, yeah, this should be our very beginning state 1. And then, yeah, this should be state 2, where it's like here. Compressing it. Probably. So if we have V, we're gonna have some V initial. Oh, but this sucks, because like, no, it's okay. I'm just gonna say like the bottom of this corner is gonna be the, all the lights just turned on, okay. The bottom of this corner is gonna be the potential energy. Or like wherever, I don't know, like here, when the center of gravity is, I think this makes it clear enough that it's like, that's 0. Wait, but no, I need to know the distance then. Oh no. Okay, that's gonna be rough. It's okay. This will be the 0. Okay. I've got it. Oh, nice. What was it? EGI plus EEI 0 plus U1 minus 2 is going to be 0 equals delta T, or sorry, equal plus TO equals VGF plus VEF plus TF. I don't know why I use I and O. I guess I should probably use O and O, right? Maybe 1 and 2. No, I don't like 1 and 2 as much. I feel like writing an O is just a little easier. Oh, wait. Wait, I have to... Wait, there is friction. Never mind. Okay. I lied. We do have friction. I don't know how to do the friction part, but we're gonna leave that part for another day. Okay, so VGO. Okay, F, T squared times 8. Okay, wait a second. Now we'll see how close I was. 0.8, that's the cosine theta. Squared. T squared. Huh. 200. Oh, gravity, yeah. Yeah, that's pretty close. Wait, so why is it T squared? Oh, maybe you just said F of T as in like it is T? Or was I not doing... Was F of T not 8? Maybe that's why I was getting it wrong. If it wasn't 8, that would make sense. That's pretty close to this. I'll take it. I'll take it as a win. I'll take it, even though I didn't get it right. You know, whatever. Okay. So we're 8 meters off the ground. Okay, the weird thing about this is like, I'm just gonna assume that the 8 meters is like the distance. Oh, but, oh no, like, oh. It's more complicated than that, isn't it? Fine, okay, we'll do some trig. So 8 meters, okay, first off, mg times, we have 8 meters times sine 20 plus delta x times sine 20. That should be how much we compress it. Is that true actually? delta x. Okay, wait. No, 50 meters minus delta x times sine 20. 50 meters minus delta x sine 20, I think. It's 8 on the y and 8 on the x. Oh, I see. Yeah, that makes sense. Oh, did I flip the two numbers? Did I flip the sine and cosine? I might have done that. On the x. Let me see. Wait, would that give you the right answer? I don't know, maybe. Doesn't give me the right answer if I flip them, but I don't know. Anyway. Okay, that's our VG0. I think things are gonna cancel out, which will be nice. And then VGF equals mg, and that's the 50 meters minus x, delta x, times sine 20. Yeah, so that'll cancel, which is good. Which I guess makes sense, but I guess it's good to kind of think about that. Oh wait, no it won't. Plus... Why's my brain like... So I'm thinking about it, it's like, you're gonna... Unless you're perfectly in the middle, wouldn't it not be? Okay, we'll figure it out. Knowing the velocity of the package, okay. So we know t0 equals 1/2 m b squared, or 2 squared, and I'll just do that. And then tf equals 0. Great. We know that VEF also equals 1/2 k delta x squared. Okay, well that should be everything, except for friction. So I'm not gonna do friction. Well, friction is like what? It's like k x negative x. I don't know, something like that. I think it's literally just friction times distance. But I could be wrong about that. I would need to get the normal force, and I don't really want to get the normal force right now. I think I'm gonna call it here. Thanks everybody for hanging out. We did some physics, we did some other physics. Where's my thing? Beep. There we go. Yeah, I'm gonna try and stream again sometime soon, because I wanna do more problem set stuff, because I have problem set stuff. And yeah, I might as well do it on stream and hang out with you guys while I do it. All right, I'm going to head out. But yeah, have a nice day. Everybody stay safe, eat well, sleep well, stay hydrated, and I will see you next time, whenever that is. All right, bye.